Okay, so let's start. Welcome everyone to another session of India ML Trading Group. And today we have with us Soumyadeep Roy from IIT Kharagpur, and he will be presenting his recent work, which is MEDVOC, Vocabulary Adaptation for Fine-Tuning Pre-trained Language Model on Medical Text Summarization, which got accepted recently in ICHKAI 2024. Before Soumyadeep will start his presentation, I'll give a brief introduction of Soumyadeep. Soumyadeep is currently a PhD research fellow in Department of Computer Science and Engineering at IIT Kharagpur, and he is supervised by Professor Niloy Ganguly and Professor Samik Sural. He is part of complex network research group Synergy at IIT Kharagpur. He is passionate about interdisciplinary research on medical NLP, fast pretending of gene transformation models, and adapting LLMs for medical question answering and summarization, particularly in limited data settings. His works has been published in various prestigious venues like ICHKAI, SIGAR, ICAI, CIKM, IEEE, ICDH, website, ACM transaction on the web, TWEB, and he has received several recognitions in the forum of Best Graduate Forum Presentation Poster Prize at IndoML 2024 and Best Student Paper in IEEE ICDH 2023. He has spent 2.5 years working as a research associate at the Leibniz AI Future Lab L3S Research Center in Germany with Professor Wolfgang Nigli in collaboration with Hanover Medical School, Germany. And he has developed a novel machine learning methodology for identifying novel patient subtype for Parkinson disease. Before joining PhD, he has completed MS research also from the CSE department at IIT Kharagpur. So over to you, Soumyadeep.
Yeah, thank you, Kishalai, and also for organizing this reading group and inviting me here. So I am audible, right?
Yes, you're audible. Yeah.
Okay, then I will start the presentation by
Yeah.
sharing the screen. Okay, so the
Yes, we
slides are
can see
visible
you.
and it is moving.
Yeah. Now
Okay,
slides are visible and it's moving also. Yeah, I can start. Yeah.
great. So, okay. So today, so welcome everyone and everyone from the audience also who has joined this session. So today we will discuss our work called MEDVOC, Vocabulary Adaptation for Fine-Tuning Pre-trained Language Models on Medical Text Summarization. So this recently got accepted in ICHKAI 2024 in the main track. So this is a joint work with Gunjan, Balde, me, Professor Mainack, Mondal, and Professor Niloy Ganguly. All of us are from IIT Kharagpur, but I'm also affiliated with the L3S Research Center at the time of that work. Okay. So let us start from very basic. So what is a typical medical question summarization look like? So what we have is that, suppose, let us take this example. So you are given, say, knee osteoarthritis. Good morning, about 20 years ago, and this is a long text that is given to you. And so this is from a question summarization task. So this is like posted by a patient or a caregiver of the patient, and the task is to summarize it. So this will be summarized as you saw below, like how can I find physicians or hospitals who specialized in knee osteoarthritis. So let me first formalize what summarization is. So this is known as the source document. That is the starting document on which you summarize. So this can be a single document, like in this case, or it can be multiple documents. And sometimes, usually, you have a question and you extract the relevant portions from either the multiple documents or a single document. So here we consider a single document. Then you are given a reference summary. So these reference summaries are usually written by humans. So this is, since it is medical, so these are written by medical experts. And you then have the generated summary, that is the deep learning models that we develop. So they will be used to generate the summary. Like, I think most of you are familiar with that. And so this is generated by the uh, model. Now, to compare how do we perform, or when we evaluate, how do we evaluate? So we take the generated summary and see how close it is with the reference summary. So close can be by through various metrics like overlap, or the other metrics are also possible, which we later discuss. But this is the problem formulation. Okay. So now let us go one step further. So how is this medical summarization problem is nothing new, but how is it solved till now, right? So what we have is that this is the typical summarization pipeline that we have. So you have um, pre-trained language models like BART, Pegasus, and then you train it on this summarization stuff. So this is the pre-training step. This is pre-trained, and now you have to fine tune it for the task of summarization. So there is one difference. So if you think in the classification setting, what we have is that we directly fine tune on the target downstream task. But in summarization, we have to teach it some more. Why? Because this set is quite small. Like this target or downstream data set that we have, which is a summarization data set, is around say 1,000 points. So this is not enough for the generation setting. That's why what is done is that these pre-trained language models are first trained on the summarization task. And in this case, it is this CNN Daily Mail. So this is a news summarization data set, and you can see it is very large, 300 key points. So the summarization task is taught, which is referred to, will now onwards referred to as the intermediate fine tuning, because this is not the target task. And then once it knows how to summarize, then we again fine tune on a smaller data set, which is the medical data sets in our case are of size say 700 to 2000 data points. And so this is what a typical pipeline looks like, right? Now let us try to understand what are the problems that can arise, and we will try to show that we mitigate one of those problems. So first you can see that since the intermediate fine-tuning dataset is CNN Daily Mail, which is a news summarization dataset, and it has certain properties. One property is something known as the lead bias. That is, since these are news articles, so what it does is that it takes the entire news article and the headline, it considers that to be the summary. So this is how it is created. So if you understand how our news is written, so generally in the first paragraph, most of the crux of the news are there. That's why these reference summaries, when they are trained, they introduce something as the lead bias. So in their papers, if you see, there is this lead 3 or lead K, which just selects the top K sentences, and that is like a very strong baseline. But in case of biomedical, this is a problem, which I'll come to why later. Second is uh, this is since it's a news summarization data set, you can intuitively understand that when you do it on medical, you will have a very huge vocabulary mismatch, a domain mismatch. So this we quantify here. Particularly, we focus on the vocabulary overlap, right? And what we find is that, so this is CNN, that it has a very low vocabulary overlap, which means that since this model vocabulary used to tokenize, it can lead to a lot of problems at the tokenization level. So the simple idea is that it has a very high vocabulary mismatch, which is expected, because whenever you go from a say open domain to a legal domain, suppose it has a high mismatch, to a medical domain or any expert domain per se. So this is the two key ideas or the key limitations of the prior method. Now in this paper, we'll focus on the problem of vocabulary mismatch. And what we see is that vocabulary mismatch is fine, but what does it lead to is the negative impact. So what it leads to, it leads to poor tokenization. So if those words are not present in the vocabulary, so how these models are treated is that first this entire say text is given as input, then it goes through the tokenization step where there is a tokenizer of the given pre-trained language model and the corresponding vocabulary. So if those words are not present in the model vocabulary, so it will break it down into subwords, or it will try to find the closest subword that matches it. What we find here is that we focus on which words are split a very high number of times. So suppose words that are split 4 or more times. What we found that we focused on them and tried to understand why it's happening. And what we found is that most of them are almost always these are medical words, as evident from this word cloud. So you can understand. So this is not a medical phenomena. This is an expert domain phenomena. Whenever you go to an expert domain, you will face this issue. Now let us go one step further and to understand how the mismatch happens. Suppose you have the word erythromycin, right? Now in the current vocabulary using PLM, what we find is that it is now broken into ER hash hash YT hash hash HR. So you can see into 5 such subwords, right? And the problem is that when it is splitting into so many times, it has two main effects. One is on the encoder side. So what it's done is once it is broken down into subwords, to get the final representation of the word, you generally average it or some kind of accumulation step you do. There, since these are split into a large number of times, the meaning goes away that way. Second, at the decoder side, if you think when you are trying to generate some words, you also generate at the token level, right? So if you have to generate a medical word or an important word of the particular domain, and you need to generate consequently 5 such subwords to generate the right word, versus if you have to just generate in say 2 subwords or an exact word, it is much easier. So this is the second problem that happens, that for a important domain word, like in our case medical word, you need to generate more number of subwords, right? And so these are the two main impacts that a high vocabulary mismatch happens. So current methods, they do something known as domain adaptation. That is, they update the weights, like you have heard of, say, BioBERT or Clinical BERT. The other kinds of models are there, where they generally what they do something known as continual pre-training, right? Where, say, suppose they take the original BERT model, which is trained on, say, Google Books or like the open domain, and then they take, say, PubMed articles or some biomedical literature, lots of it, and they perform an unsupervised objective like the mass language modeling, say, and that is what they call as continual pre-train, right? But they do not update the vocabulary in the process. So the final step on the fine-tuning stage, when it goes to, it works with the same vocabulary, right? So our aim is that, or what we are trying to establish is that we need to update the PLM vocabulary by adding the vocabulary from the target domain. So there are many works in this direction, but all the works are limited to the classification setting. The people have worked on this angle, but from the classification setting. Like there are papers like Avocado. But what we find is from the summarization setting, to the best of our knowledge, there is no such work. That's why our idea was that, okay, can we use the learnings from these vocabulary adaptation measures and do it for the summarization task? So how do we move forward? So as we explained, the top one is the existing setup. Like you have the retrained language model, then which you do an intermediate fine tuning on the CNN Daily Mail set, and which you have on, then you do fine tuning on the target task or the target medical summarization task. So we have two steps. First step is that instead of CNN Daily Mail, we replace it with something known as the biomedical article title generation task. So what we find is that when we are trying to teach summarization, there is no equivalent large scale medical summarization datasets available. Like CNN Daily Mail is say 300,000 sites. So we do not have any such equivalent from the medical perspective, right? The closest that we have is something known as the Medline database, where it is like you give the full text of the article and then abstract is the your summary, right? So which is very, with a lot of different characteristics. So what we establish in our work is that if we take the task of biomedical article title generation, that given any article, so the metadata is always available, meaning the medical, the paper title, the paper abstract, and the authors and other metadata are always available. And it will be available in any generated field also, any expert domain field also. And we posit that if we consider that as the summarization task, it is equivalent and will be a good intermediate task to teach it summarization. This is what we establish. But why will that work? So this is what we propose as our first novelty. is that we propose that because these biomedical articles are available in plenty, like the PubMed, any like the huge bases are available, because we are just looking for the abstract and the title, which is kind of the metadata. We are not interested in the full title, the full text of the paper. So this will have in large quantity, and you can understand this is also generalizable to other domains. If you go to other domains, you will also find lots of such paper metadata availability. So you can apply this method also. But why does it work? We'll come to that. But let us see what changes it brings in. So the change is simple, that once we have reference summary, this is the correct reference summary. This one was generated by CNN Daily Mail, and the third one was generated after you just make this one change. So we have not updated the vocabulary yet. So as you can see, it is still VPLM. So VPLM is the existing vocabulary of the pre-trained language. We have not yet updated that, but we'll update it in the next stage. And what we find is in this stage, it has some like medical concepts, which is nowhere mentioned in your reference summary, but it is but they are mentioning it. Whereas in PAC, although it is not the correct reference summary, because it is they are talking about treatments, whereas the reference summary is talking about physicians or hospitals, but it is better in the sense that it has identified the the objective to be osteoarthritis of the knee, which is also what the reference summaries are. Knee osteoarthritis is. So there is some improvement, but it needs to be improved further. So I hope I am able to put across the first intuition that we have and the proof of it. Now we'll go into little detail as to why did we choose this task. So this is not like something random. What we wanted to do is understand what is a good intermediate fine-tuning task. So intermediate fine-tuning is a well-established topic, and there are works that tell what are the characteristics of a good intermediate task. And the basic framework is that it should closely mimic what your downstream tasks are. And that is what we tried to find out. So let's go step by step. The first thing, if you remember, when we introduced in the limitations portion, was something known as the lead bias, which CNN Daily Mail has. So what is important part in the PubMed abstract or in the medical domain is that if you take PubMed abstracts, so usually the most important results remain in the conclusion and the results section. So which is usually at the end, right? So this is one very different characteristics, and this needs to be like trained or informed to the model, which if we train with CNN Daily Mail, we were not doing. So this first part takes care of the lead bias. And if you see the figure on the right, it is also evident. As you can see, the highest shift occurs towards the ending portion. So this shift is like the difference between what you observe in the positional embedding that you had, right? And we see a huge shift in the uh, token index after 400. So this is like, this has the limitation of 512. So this is the, that is the what this signifies. So it mainly signifies an effect of this by this intermediate fine tuning step using PAC, that is the PubMed abstract collection, is that the positional embeddings are now more focused or give more attention to the ending part of the document, that is the source document. This was the first set of results which supported that okay, why biomedical article generation is a good step. Now the second characteristic is that are they mimicking the characteristics of the downstream tasks? So because that was one point of what a good intermediate tasks are, and we find that is the case. So it is more similar to the source document length of EBM and BioSQ. So EBM and BioSQ are our two medical document summarization tasks, and MakeSum and CheckSum are two medical question summarization tasks. These are the four summarization data sets that we have. And we find that they are mimicking the property, like the source document length in this case, the RS length in case of MakeSum and CheckSum, and the abstractive nature in case of PAC. So which is the bigram overlap that we have between the source document and the RS. So this means that in case of medical text summarization, you can use biomedical title generation. But this method is generalizable to other domains. Suppose if you go to legal, And there, if you find that these properties are holding, then you can directly apply. But if you see these properties, that is uh, closer characteristic with the downstream does not hold, then you cannot apply this method. Okay. So this was the first step, that we now moved our characteristics towards the downstream task and also towards the medical domain, right? By our intermediate fine-tuning step, which we replace with pack. So this is our replacement. But if you remember, it was still VPLM. Like this is still the same. So we have not updated the vocabulary, right? Now we'll now focus on updating the vocabulary. So what we now say is that this vocabulary needs to be updated, and we have established why we need it to be updated in our first part of our presentation. And simply then VMedVoc, which we now refer to as VMedVoc, will be a function of the original uh, pre-trained whatever vocabulary that we have of the original model. Second, it will take into consideration the important vocabulary that is extracted from the target dataset and the pack dataset, that is the intermediate tuning dataset. So this is the overview, that this is what VMedVoc is. It considers all the three sources in mind while constructing the vocabulary. So this is the general overview, and we will next go into each step in detail. So if you can see on the top is that the only change we have in the pipeline now is that we, instead of VPLM, we'll now have VMedVoc. And I will briefly give an overview of the method so that it is easier to understand. So it is quite simplistic in the sense that what we do when this, what we simply do, we take the medical, so we have the pack dataset, we have the target dataset. On pack dataset, we identify which words needs to be split. So this, which we'll take into consideration. Since it is a medical domain, and since we find that medical words are largely split, like it is split most amount of times, we focused on medical OV words. What does an OV word mean? An OV word is given a word, if that word is not exactly present in the vocabulary, meaning the tokenizer, the current tokenizer with the current vocabulary splits into more than one subword. So that is a OV word in our case. We select all the medical OV words. We go to how do we select later. And then we identify what, use the model's tokenizer to generate the candidate subwords. This is a simple step. And these are the candidates. And now we build on top of that. So when we have to build on top of that, meaning we have to find an optimal setting. But if you remember, what was the main problem is that you have this big intermediate fine tuning step, and this step has 300K data points. So this is not a simple fine tuning step. Like in classification setting, your fine tuning data set is very, very small usually. But here, when you have to fine tune, you have to also fine tune the pack part, right? So that's why, and which is very, very big. So if you have to repeat the same hyperparameter search step or hyperparameter tuning step like we do in classification, it will not be possible in this case. And that is one of the key reasons why there are not a lot of works in the summarization setting, because this intermediate step is huge. So if you do the hyperparameter search, then it will become very, very, very costly, right? So we introduce a hypothesis known as the fragment score, which will come into detail. So the fragment score is an unsupervised method which does not require this huge intermediate tuning step, right? To identify which is an optimal setting. So the optimal setting is what? Given VPAC and given V target temp, what will be the set that I add? So if you think this entire step, this is some combination of VPAC and V target temp, which we finally add. The VPLM remains, as the original vocabulary is there. We simply append it to the end. So this entire step, which will go into detail, is just some function of these two, that how will I add? And that we define it as a hyperparameter search step. And what does it help? It helps us to, because it is, we are just optimizing, we are not hard coding anything. We our method is generalizable across different model types on BART, Pegasus, and Bursum ABS. And we do not have any hard coding, which was a problem in the prior methods where they only focused on one model type. For example, if they develop a vocabulary adaptation model for say BART, you'll only see variations of BART, which has the same model vocabulary, and then they have some hard-coded threshold, which so this was an extra novelty that we could generalize to different methods because we have a hyperparameter search objective inside. And finally, this MEDVOC gets updated and added to the top, right? So given this brief overview of what our method is, I will go into one by one in detail. And yeah, that's starting. So first point is generating the subwords. Like we said, we generate one set from PAC model and one set from the target dataset. How do we select? We select the medical words that are split more than one, that is medical OV words. And how do we identify they are medical? We use an existing tool called QuickMLS that, and based on certain put a very high threshold of 0.95 and say it is a medical subword. Because yeah, now what we do, we have this set of words which are medical OV words, and then we pass the existing tokenization scheme of the existing model, because that is how they create the subwords. And therefore we get, so from the word level, these were candidate words. After running the tokenization step, usually byte pair encoding steps, we get the candidate subwords. Like for target, it gets v target temp. For pack, it is the corresponding v pack. Right. Okay. So now what we found that, so what would be the best case, right? So because our target task is this v target, that is the medical summarization task. If we just consider this, then it would be fine. There is the simplest step that we are targeting a particular summarization task, and only based on that task, whatever the vocabulary is, if I add, that would be fine, right? But the problem that we found that this target vocabulary size is very, very small. And so if the model vocabulary size is say 50,000 for BART, we are say adding say 500 words, it is very small and it will not cause a change. And that is what we saw in the results. That was the problem number one, that why we could not just use vtarget. Second is that now the idea is, okay, if we just could not use vtarget, what else we have? We have vpack. So now the idea comes, can we use vpack, right? Therefore, that is the two ideas. And the third idea is, suppose we add these vocabulary, how will they get trained? They will be first given some random embeddings. So the embeddings will be randomly initialized. And then through this intermediate fine tuning step, they will get the values. They will get the right embedding. So what you can understand, if you have to select which words you will add, it is dependent on how well it gets trained using PAC. That's why the intermediate fine-tuning dataset plays a very big role in this. So we have to use PAC. So the second use of PAC is to use it for refining our target vocabulary, because there can be some subwords from vtarget which are very rare. But because you are using PAC to train it, so if it is not enough times present in PAC, you will not see good context, and you will learn a poor embedding. So that's why we use PAC to further filter it. Next, so we now get what we have. We have now vtarget temp and vpack. These are the candidate subwords we have. Now our task is to perform this hyperparameter search, that is which combination of vtarget and vpack to take to start with. So to start with, we can see, since pack is very big, like 300,000 in size, vpack will be significantly big, whereas vtarget is anyway very small, right? So then what we introduce is that for hyperparameter search, we introduce these two different parameters known as K and A. K determines, so if you see pack, so for example, vpack that is getting added, so it follows the tokenization algorithm. Suppose it follows byte pair encoding algorithm. So from the top end part, it chooses the one which has the same most highest frequency, right? So it is automatically ordered in that way. So what we do say is that we choose the top For example, if it is 5K, we only consider VPAC only the top 5K as part of VPAC. We do not consider say 30K, 50K. VPAC is very big, right? We only consider the size of VPAC to be the top 5,000, and this we go up to the size of VPLM because we don't want to add our vocabulary that is more than the original size of the model, right? So this is K determines that size and A determines that what fraction of V target should we add, because V target is small, I understand, but when you're adding VPAC, it may happen that VPAC can overshadow V target. That's why we wanted to keep a filter, or we wanted to keep conditioning over V target. So this A is that ratio, and this ratio ranges from 0.25, where VPAC will be smaller than V target, but up to 10 also, because in question summarization datasets like Mexam and Checksum, we found that V target is very small, like say 200 or 100 in size. There you need this high ratio so that the V target, the final V MEDVOC, you are adding sufficiently in comparison to VPLM. So that's why for document summarization, this is usually very low, but for question summarization, it is usually quite high. So this is the two unique parameters that we establish for our hyperparameter search. And right. So now for different values of K and A. So suppose you have some K and you have some A. So mainly you have a new vocabulary, right? But how do you test it? So you have to do hyperparameter tuning, meaning one combination, you have to do intermediate fine tuning using the new vocabulary that you have added. So um, so this step, so you have say a new vocabulary, you have a V medvoc setting 1, right? So now to understand whether it is doing good or bad, what you have to do, you have to train it in this step, followed by fine tuning on the smaller target dataset. Then you will get some summarization performance on the validation set, suppose, right? So this step is a huge step, right? So if you have to, and each step on average requires 45 hours. So this is averaged across the 4 datasets that we have and the 3 model types we have. So we have Bursum ABS, BART, and Pegasus. On average, it is 45 hours. And so 240 combinations, suppose there is the minimal combination we can take in hyperparameter search, will lead to 450 days, which is infeasible. And this is one of the main limitations why there are not so much works in vocabulary adaptation for summarization setting. So what we said, that we introduce an hypothesis that, okay, give if we are able to do step, this is the fine, we will get the best setting, right? But can we approximate the best setting by an unsupervised objective? So this is known as the fragment score. So fragment score is a very simple thing, that given the current vocabulary that you have and the current tokenizer, on average, how many subwords are each word broken into? This is known as fragment score, right? And this fragment score has been used by existing vocabulary adaptation methods for classification for those settings. So we thought, okay, if that is working in their case, let us see if that works in our case. And what we found is that it actually works, meaning that when we see that we optimize the fragment score, it correlates with optimizing the downstream medical summarization performance. This means that we no longer have to go through this intermediate tuning and fine tuning step. We just have to compute this fragment score, right? And if you can see this fragment score, it is not dependent on any word. So it is just on the corpus level you are doing. You need a vocabulary and a corpus to determine the fragment score. And this is done on the target summary, right? So what we observe is that this leads, okay. So now what we have done hyperparameter search over 240 settings, right? Based on our method, it takes 5 hours 45 minutes time just. This is the maximum time taken. So we do not have to do this 240 combinations and just take 6 hours time on average. So because we are adding this vocabulary, does that mean the compute goes down? Because there is usually a trade-off. So what we found is that we can add this step, and this requires only an additional time of say around 6 hours on average. and the amount of parameters that is have. If you see the percentage, it is marginal. Like in Pegasus, we are just adding 0.15% of extra parameters. For BART, it is 1.15%. For BERSAM ABS, it is 1.59%. Why? Because only we are adding this embedding matrix for corresponding to this extra words that we are adding, and that are randomly initialized, right? So MEDVOC leads to marginal compute overhead. And yeah, so now let us go into the evaluation setup, and this will become more clear that why it is important. So if you see prior methods on, say, vocabulary adaptation on the classification setting, they only focus on only one model type. What do I mean by model type? So suppose if they use BART, they will say I have introduced another model called, say, BART plus plus, which has the same model vocabulary, but some changes are there, and they try to evaluate there. And they have a fixed threshold, either based on fragment score or on the number of words that are added, right? But here what we show is that since we have this hyperparameter search step, we do not need any such hard coding. The algorithm automatically identifies the optimal setting, right? So, and that's why we are able to test on 3 different model types, and you can see they are vastly different. So if you see BERSAM ABS, the pre-trained language, like the PLMs vocabulary, original vocabulary, is only of 30,000 size. BART is of 50,000. Pegasus is 96,000. Each of them have a very different tokenization scheme. So you can understand that these are very, very different models, and the hyperparameter search is able to capture those characteristics and identify the optimized setting, right? We evaluate on 4 medical summarization tasks. One is document level, and another one is on question level. And these are all standard tasks. We show on standard metrics like RUGEL, BERT score, concept score. The concept score takes into consideration the faithfulness of medical summaries, because these are medical summaries. Faithfulness is an important aspect. BERT score takes into consideration the semantic similarity, whereas RUGE is like the word level similarity. And RUGEL is generally the standard metric that is used. We also do an additional step. So I had told from the start that these vocabulary adaptation models were done in the classification setting. So mostly or always in this encoder only models. So for summarization, we focused on encoder decoder models, right? So what we thought, okay, so whatever they have done, we could do only on the encoder side. And when we do the intermediate fine tuning, it will automatically go over to the decoder. So we can just change the encoder portion. And that's why we took those models, just change the encoder portion in BERSAM ABS, and also showed results. And we found that we also outperform in those cases, right? So now let us go to the brief results that on different data sets, we tried our results and we get a good performance in all the cases on average. So we focus on 2 metrics, that is the standard metrics of summarization in the medical domain. One is RUGEL, because it is not RUGE1, it is RUGEL is the standard metric, because um, if there are some words missing and RUGE1 may be very high, but that may significantly change the meaning of the sentence. And in medical, that's why automated metrics may not help so much. That's why RUGEL takes care of that you requires an exact subsequence match. And concept score checks the faithfulness. So this is like you extract the medical concepts from both summaries and you just take the overlap with how much it is. Yeah, so this I talked about the vocabulary adaptation methods. The most recent one is Avocado. They also use this fragment score based method, but they test on only one vocabulary type. This is only on classification they do. So, and they also keep a fixed threshold. Like in fragment score, if you see our fragment score, the algorithm we did not discuss in detail, but if you read the paper, you will see that we choose the optimal fragment score, but we also optimize for the vocabulary size by checking the neighborhood. So the fragment score is not, there is no fixed threshold. It automatically, where it plateaus, we select those portions. But in Avocado, they have taken a fixed threshold of fragment score. PubMed bot is well known, so we just change the encoded part of BERSAM maybe, and we show the results also. And we see we are doing better. Okay. Now we slowly move towards the key hypothesis which we started at the start. That was high vocabulary mismatch. And we said that that is what we'll focus throughout the paper. Now, if you think from that perspective, then which are the settings where the vocabulary mismatch problem will be the highest, right? So from that perspective, we thought there are two settings. One, where there are very, very high amount of OV. High meaning with respect, like in terms of percentile. There is, of course, no fixed limit of OV, but within the data, what is the, say, top 10% or top 20 percentile? Those are like high OV words, high OV documents, where let us see whether it is actually working or not. And second will be longer RS. So in question summarization, suppose these are very short generations. So maybe it is not such a difficult job to generate in that way. But when you have to generate very long reference summaries, like in case of BioSQ and EBM sum, we select that subset to evaluate, okay, when it is generating long summaries, does our method help, right? And we found that in these two extreme settings, we show better, much better performance, right? So to say is that whatever we are proposing, that effect we are somewhat seeing in our results in that way. Now, since this is medical summaries, automated metrics are also very good for the benchmarking part. It is, you always have to show the medical human evaluation, but by medical experts. Because even if they say the medical metric, even if you say the Rugel you got better, but the final summary still does not make sense. It does not make sense. So that's why we also performed a human evaluation where we randomly selected 100 such data points and we asked medical doctors. So you use the prolific platform to recruit medical doctors. So for each of the 100 sample points, it was annotated by 3 separate medical experts and on these 3 metrics of coherence, relevance, and faithfulness. And as you can see, so these are, we use this Likert scale of 1 to 5, and you can see the like breakup of that, right? So if you see MEDVOC, that is on the right hand side, that is the slashes, we have a higher portion of 5 as and higher portion of 4, right, as compared to uh, the CNN Daily Mail model in that. That is the original model, that is the existing state of that that exists, right? The same thing we do much better in relevance. And the most important result is on faithfulness because this is very important from the medical perspective, right? So, so these were the main results. So let us understand what were the key takeaways. So this was like the first work that showed that vocabulary adaptation during fine tuning is essential for summarization. And here we focus on the medical domain. But as we repeated it at the different junctures of our talk, is that this method is generalizable to the other expert domains where there is a high vocabulary mismatch. But those characteristics must hold, right? We evaluated on an extensive set of we did extensive experimentation by going across 3 model types, which are very unique, like in terms of like a vocabulary size, a tokenization scheme that they use, and also across 4 datasets. One are document summarization, another one is the question summarization. We also evaluated in the extreme cases of vocabulary mismatch issue, maybe the highest, that is high OV setting and long form generation, and we found it to be working better. We also show results in the paper on 0-shot and few-shot settings of summarization, and there we do better in most cases except for BioSQ. Uh, we also evaluated using, we also performed human evaluation using medical experts, where we found the summaries to be more informative, that is higher relevance score as we showed, and more faithful, that is higher concept score, or this portion, the higher faithfulness, right? The preprint is available and the code base, we also make the code base public. I want to acknowledge Complex Networks Research Group at IIT Kharagpur for providing the environment and the resources for the work. Also L3S Research Centers, as I was, when I was starting NIGS, I was affiliated with it, and also they provided a lot of the server resources. Um, yeah. And thank you for listening. I also want to thank the audience here for giving their time to listen. And if you have any questions, I am happy to take them.
Yeah, thank you, Somodip, for this nice talk. So I just have one question that this intermediate fine tuning, what you were talking about, I mean, what is the benefit of it apart from just retaining and fine tuning? Why we need an intermediate fine tuning?
So it is required because these pre-trained language models, so when you have to teach them the summarization task, uh,
Mhm.
the so you need to teach them the summarization task. In the classification setting, what we do, we have say a small amount of 1,000 data points, and
Mhm.
that usually is enough. But what is seen in the summarization setting is that if you just train it on the say 1,000 target data points, like data summarization data sets that we have, it hugely overfits the model and leads to a poor performance. So this is like a standard setup in summarization, where if you go for say non-medical summarization also, they have this intermediate step, because you have to teach them the summarization task, and for that the model needs a lot of more data points to train. So yeah, so for classification you
For,
need lesser points to train, but for summarization you would need it to teach with a lot more number of data points.
so it's specifically for the summarization task. I mean, not
Yes,
for
yes.
other tasks. Or is there any other
No.
task also where it can be done?
Um, so I will say, at least I know for the summarization part, that's what we
Okay.
started mentioned at the start, that what is the existing setup. Like in the existing setup, you have the intermediate fine tuning using CNN daily mail, but that we then
Okay.
replace with our method. So that was a standard setup that we have the summarization. But I think it will also be true for other generative tasks also.
Because you are mentioning that this intermediate fine tuning data set has to be close to the downstream data set, right?
Yes,
I mean,
it
the
has to
similar
be
to the
yes, yes. The characteristic has to be somewhat similar. Yeah.
is there any question from the audience? Yeah, I think there is no such question. Let me check in the Q&A session also. No, there is no such question. Okay. Thank you, Somadip, for giving your time and attending the and giving the presentation in this reading group. Okay, then let's
Yeah. Thank
wrap
you
up
also
this
for
session
like
and
inviting me and also like listening to the talk. Yeah. And all the best for organizing
okay.
this reading group also.
Okay, okay, bye. We will meet next week.